It's wild to think that the stuff of like sci-fi movies, quantum physics is actually the backbone of so much of the tech we use every day.
Yeah, it really is.
I mean, think about it. Lasers, scanning groceries at the checkout, atomic clocks, making sure our phone's GPS is on point.
It's mind-blowing when you stop and think about it.
Right? And at the core of all this, there's this really bizarre phenomenon called quantum entanglement.
Entanglement. Einstein called it spooky action at a distance. And for good reason.
Spooky is right. It's basically like two tiny particles are so deeply connected that if you measure something about one, you instantly know the same thing about the other.
Exactly. No matter how far apart they are. It's like, imagine two coins that always land on the same side, even if you flip them miles apart.
Totally. And what's even crazier is that something so strange actually has real-world applications. And that's what we're diving into today. A recent breakthrough in entanglement that could lead to some seriously cool tech advancements.
Just pretty exciting stuff.
So, for those listening who love to get the inside scoop on complex topics quickly and thoroughly, get ready. We're going to break this down in a way that'll give you those aha moments, without overloading your brain.
Exactly. We'll keep it clear and engaging.
Deal. So let's start with the basics. Entanglement. It's been puzzling scientists for ages.
Oh yeah. Decades of research and head-scratching.
Right. And a big turning point was this thing called the Bell test.
Oh, the Bell test was crucial. It basically proved that entanglement isn't just some hidden classical correlation. It's a genuinely quantum thing. It's not like the particles had a secret agreement beforehand or something.
Right. Like, it's a much deeper connection than that. And of course, we can't forget the 2022 Nobel Prize in Physics.
Oh, absolutely. A huge moment.
Right, awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for their groundbreaking work on, you guessed it, entanglement. It solidified its place as a cornerstone of modern physics.
It really did. Their experiments were irrefutable proof that entanglement simply can't be explained by the classical laws of physics that we're used to.
So cool. And a lot of the early research focused on these things called maximally entangled qubits.
Right. Think of these as our perfectly synchronized coins, but in the quantum world.
Qubits, those fundamental units of information in the quantum realm.
Exactly. And in this case, they're sharing the strongest possible quantum link.
So that's like the perfect scenario, right? Perfectly in sync quantum bits.
Absolutely, the ideal case.
But what about when things aren't so perfect? What happens when the connection isn't quite maximal?
That's a great question. And that leads us to this really fascinating new research out of the Institute of Theoretical Physics in Paris-Saclay.
Yeah, tell us about this.
Well, these researchers have been looking into what's called partial entanglement. It's where quantum objects are still correlated, but not to that maximum level. The quantum connection is there, it's strong, but not, fully cranked up.
So it's like our coins might land on the same side most of the time, but not every single time.
That's a really good way to think about it. And the researchers, Victor Briesian and Joan-Daniel Boncal, they figured out something pretty ingenious.
Right.
They basically discovered that we could actually understand these partially entangled states using what we already know about maximally entangled ones. They found a mathematical transformation. It's like finding a common language between two different dialects.
Oh, interesting. So we know one dialect, maximal entanglement, really well. And this transformation helps us translate that knowledge to understand the other dialect, partial entanglement.
Precisely. And this gives us a much broader view of entanglement beyond just that extreme case of perfect synchronization.
Okay, I'm with you. So instead of just seeing black and white, we're now seeing all those shades of gray in between.
Right. But this isn't just some abstract theoretical thing.
Right. So how does understanding these imperfect connections actually matter?
In the real world, creating perfect, maximal entanglement is super tough. Quantum systems, they're really sensitive to any kind of interference, noise, you name it.
Yeah.
So most of the entangled systems we actually create in the lab, or that would be used in future technologies, they're probably going to be in these partially entangled states. Being able to understand these states is way more realistic. It's how quantum systems actually work.
That makes a lot of sense. So this is about getting real with quantum mechanics. Less theory, more practice.
Exactly. So it begs the question, how does this new understanding of partial entanglement actually translate into, tangible advancements in technology?
Yeah, because the reports we saw suggested this could be a pretty big deal.
It could be. One of the most promising areas is in something called self-testing methods for quantum tech. You see, in classical computing, we have ways to check if our hardware is working properly. But with quantum devices, It's a whole different ballgame. They're so complex, so unlike anything we're used to.
Right. It's like, how do you even know if a quantum computer is doing what it's supposed to be doing?
Exactly. And that's where self-testing comes in. It allows us to validate the performance of a quantum device just by looking at the data it produces. We don't need to know all the nitty-gritty details of what's going on inside.
Wow. So it's like knowing a car is running smoothly without needing to pop the hood and inspect every part just based on how it drives.
Exactly. And a great example of where this is really important is in quantum cryptography. That's where the security relies on the laws of quantum mechanics. Robust testing there is absolutely critical.
So you're saying it's like being able to trust that your super secure quantum communication line is actually secure without having to take the whole system apart and analyze every single component.
You got it. And previous research showed we could self-test maximally entangled pairs of qubits, but remember, that's kind of the ideal scenario. And this new research, well, it's a big step forward because it extends self-testing to situations with partial entanglement. Since we now have a better mathematical handle on how these imperfectly linked quantum systems work, we can design tests that don't need us to know exactly what's happening inside the device.
Okay, so instead of just being able to check the perfect quantum device, we now have ways to assess things even when they're a little, let's say, less than ideal.
Precisely. It's about being practical.
Totally. And how does this help us in actually building better quantum tech in the first place?
Think of this new understanding as a roadmap for future experiments. It helps researchers pinpoint why some entangled setups might be prone to errors and instability in the real world. And it gives them insights into how to make things work better. What measurement choices might actually optimize the results. By being able to better characterize and understand these partially entangled states, researchers can focus on designing quantum protocols that are more reliable and predictable.
So fewer unknowns, and that's a big deal, right?
This could be a real game changer for scaling up quantum computers, which rely heavily on the reliable entanglement of many qubits to do those complex calculations. It's like we have a clearer blueprint now for how to build and control these incredibly powerful machines.
It's not just about quality control after the fact. It's about understanding the basic building blocks, these entangled states, so well that we can engineer better quantum systems from the ground up. Which brings me to the question on everyone's mind. Why should we care about all the intricacies of partially entangled qubits? It still sounds pretty deep in the weeds of theoretical physics.
You're absolutely right to ask that. But the answer is, progress in understanding entanglement has huge implications for the future of technology that will likely affect our lives in many ways. As quantum computing keeps advancing, even small improvements in how we generate, manipulate, and, yes, test entanglement can dramatically boost the speed and efficiency of these machines. And let's not forget, quantum computers have the potential to tackle massive problems that are just impossible for even the most powerful supercomputers we have today. Designing new materials with crazy properties, developing life-saving drugs, breaking encryption that's currently unbreakable.
Yeah, the kind of transformative potential we hear so much about. But it's not just about practical applications, is it? This research also tells us something about the very nature of quantum theory itself, right?
Absolutely. By delving into the patterns that emerge when we're dealing with different types of entanglement, including these partially entangled states, we get a better grasp of the fundamental rules that govern the quantum world. This helps us refine and maybe even expand the very boundaries of quantum theory itself. It's like we're getting a more complete picture of what's possible at the quantum level. And this isn't just some academic pursuit, A more complete picture of the theory lets us develop even more powerful ways to explore and control all sorts of quantum systems.
And I remember reading something about a potential security boost.
Ah, yes, that's a big one. Devices using quantum entanglement for secure communication could get a big security upgrade. We wouldn't have to rely solely on the physical hardware, which can be tampered with. Instead, we could base security on real-time observations of the entanglement itself. If it changes in an unexpected way, it could mean someone's eavesdropping. It's like entanglement acts as its own alarm system.
Wow. So if someone tries to intercept a message, it would disturb the entanglement, and boom, the users are alerted instantly.
Exactly. More broadly, this deeper understanding of partial entanglement opens up a whole new world of possibilities in quantum testing, communication, cryptography, and of course, computing. It's about moving beyond those perfect scenarios and developing tools and techniques that are robust and reliable, even in the messiness of the real world.
It's quantum mechanics getting down to business.
Precisely. And one last thing I wanted to emphasize, This breakthrough really shows how closely math and physics can align when we find the right theoretical framework.
That's so cool. Okay, so let's recap what we've covered in this deep dive. We started by looking at quantum entanglement, that spooky action at a distance. Then we dug into this groundbreaking new research that's expanded our understanding of partial entanglement, which, let's be honest, is much more common in real-world quantum systems. And finally, we talked about the huge impact this has for developing and, importantly, validating future quantum technologies. More powerful computers, super secure communication networks.
It's pretty amazing to consider the ripple effect of this kind of fundamental research. Who knows what the future holds?
Absolutely. And that's where you, our amazing listeners, come in. If you enjoyed this deep dive into the quantum world and want to explore more cutting-edge science with us, make sure to hit that like button and subscribe so you don't miss an episode. We love hearing your thoughts, so drop a comment below with any other fascinating areas of science you'd like us to explore. We're always up for an intellectual adventure.
It's a big universe out there, full of mysteries.
It really is. And for those who want to go even deeper into the world of physics and technology, check out the show notes for some cool resources, which might even include some affiliate links to help support the show.
Think about it, this seemingly strange and counterintuitive world of quantum mechanics is on track to revolutionize the very technology we depend on every day. What other incredible discoveries are waiting to be made? What other secrets of the universe are out there?
Stay tuned for our next deep dive, where we'll uncover more mysteries and explore the cutting edge of science.
We'll see you there.
Until then, keep those brains buzzing.
Keep wondering. Keep exploring.
We'll catch you next time.
See you later.